is Matteo. He's associate professor at the Department of Physics at the University of Milan, and he got his PhD in '94 at the University of Pavia. He was then for a couple of years at the non-classical lines group of the Max Planck Society in Berlin, and then back to Pavia as a postdoc, and he then moved to Milan, and from 1 year ago, he was he's an associate professor. So he's working in quantum information and quantum optics. He's visiting us for almost 1 month. He will be here until the 9th of July. So if anybody is interested in speaking with him, he will be with us 10 days. And please.
Thank you very much. And good afternoon. Thank you for being here. And you know already my name. And today I would like to give a brief review of what is called local quantum estimation theory. And then I will try to give some general results and then to kill you with some examples, incomprehensible examples. And my title is Quantum Estimation for Quantum Technology, because the motivation for this line of research is basically the fact that the quantumness of physical systems is usually a resource to do something better than without the quantumness. And the examples are many, from quantum information to high precision measurement and lithography. And what they have in common, all these examples, and then quantumness, the quantum features are a resource, and we need the characterization, the precise characterization at the quantum level of states and operations. These are the general motivation of this line of research. What I'm going to speak is something specific. This is the general scheme I will deal with. And the idea is the following. I have a physical system, which may be a single qubit or a set of many oscillators. And I assume that this physical system may be prepared in several different quantum states, possible quantum states. And these are here labeled by some parameter or set of parameters, lambda. And the overall goal of what I'm going to speak about is to find a way to estimate the value of this parameter, or which is the same, to discriminate which is the actual preparation of my quantum system among the possible different several preparations. And to do this, the procedure is to prepare several times my system in the same preparation and then to perform a measure. And quantum estimation theory provides the tool to individuate the optimal measurement, in a sense to be specified in the following slides, and in turn to say which are the ultimate bounds to precision in the estimation of this parameter. And the fact that my physical system is being prepared in some state may be the result of the preparation procedures. So in this case, I'm dealing with the characterization of quantum states, or may be the result of the action of some device on a fixed known initial state. In this case, I'm dealing with operation, the characterization of operations. But of course, the two problems may be mapped into each other. So this is the basic problem. I would like to estimate the value of the parameter, labeling the state of a physical system. One may wonder that the answer to this problem is already contained in the postulates of quantum mechanics. After all, we have a physical quantity. What we have learned is to measure the corresponding observable. And the ultimate precision in measuring this observable is set by uncertainty relations. And this is, of course, true, but then two remarks are in order. And the first is practical. If you need to measure energy, from time to time, your physical system, the energy is not accessible for practical reasons, because that kind of measurement is not implementable. And the second remark is more fundamental, and there are several quantities of interest which not even in principle may correspond to an observable. Entropy, von Neumann entropy, entanglement, purity of the quantum state. All these quantities are nonlinear functions of the density of a vector. So not even in principle they may correspond to a quantum observable. And other I cannot come back, go back. Okay. Okay, no problem. And other examples are time is not an observable in quantum mechanics, it's a parameter. There is no time observable. There is no phase of the quantum oscillator observable. Note these examples. Even in principle, I cannot follow the standard procedure of measuring the observable and then look at the conservative relation. So, now again, look at the same problem. Perhaps it looks less trivial than before. So, at least it is worth to deal with quantum estimation, which is adding something to standard quantum mechanics to answer, in the general case, to this problem of estimating it. And to attack the problem, let's forget quantum mechanics for a while and see what classical statistics is telling us about this problem. So, now I have no rho is a physical system, no quantum, just a physical system. And for some reason, I assume that I'm interested in measuring some parameter, some quantity, and I cannot assess by direct measurement this quantity. I have to resort, for some reason, to an indirect measurement. So, I'm interested in lambda, and I'm measuring something else. The problem, so I prepare several times my system in the same preparation. I perform the measurement. I have an experimental sample, different value of the quantity x. And from this experimental sample, I would like to estimate the value of this parameter. The problem is naturally split in two parts. The first is the choice of the measurement to estimate the quantity lambda, and the second is the way to treat the experimental sample. So I have to measure something, I choose an observable, and then I can take the mean, I can take the cosine of the mean, I can take the cosine of each value, and then take the mean. All these functions are called estimators. So the problem is split in two parts. The first, the choice of the measurement. The second, the choice of the estimator. There is a fundamental result in classical statistics, which is called the Kramer-Rao bound, the Kramer-Rao theorem. And it's saying that if I have to estimate a quantity lambda, and the variance, which expresses the precision of this estimator procedure, the variance of any unbiased estimator is bounded by this quantity. M is the number of measurement, which is just the statistical saying, and F is the so-called Fisher information, which is built with the conditional distribution of what I'm measuring, x, conditioned to the true value of the parameter. So, here we have the answer to the problem on which is the best way to estimate the parameter lambda. The optimal measurement is the measurement which gives you the maximum of the Fisher information. So if you have to compare two different measurements, you have to choose the one with the maximum Fisher information, which is quantifying the sensitivity of the Diop distribution. You have a given value of the parameter, you have a given distribution. If you move the value of your parameter, the Fisher information is quantifying how far is set your distribution. And of course, this is to compare different measurements, but then this is an inequality. And there is a second part. What is an optimal estimator? The optimal estimator is the one saturating the Kramer-Rao inequality. So if you have an estimation problem, you have first to choose the optimal measurement, maximum Fisher, and there is no way, no constructive way to be in classical physics to build the optimal measurement. And the second is to find an optimal estimator. And again, we have no theorem to find the optimal estimator. But at least we have a couple of examples. And the first example is the Bayesian estimator. Once you have chosen a measurement, and then you have to choose the estimator, how to treat, to process data. And hopefully with the idea of saturating the Cramer-Rao inequality. And the first estimator, which at least in the asymptotic region is always optimal, which means it saturates the Cramer-Rao inequality, is the Bayesian estimator. If you measure the quantity x conditioned to the value of the parameter, then you are interested in the distribution of the outcomes given the experimental sample, and you follow the standard Bayesian recipe, and the Bayesian estimator is just the mean of the a posteriori distribution. There is a nice theorem. The Laplace theorem says that in the asymptotic limit, if you perform many measurements, the a posteriori distribution is a Gaussian with a variance which is the saturation of the Cramer-Rao. So at least in the asymptotic region there is always an optimal estimator. And there is another example, which is the maximum likelihood estimators, and again in the asymptotic region you have optimality in the sense of saturation of the Cramer-Rao. Okay, this is what is known from classical statistics. You have to maximize the Fisher information, no theorem, no constructive way to do this. And then you have to find an optimal estimator. At least in the asymptotic region, we know that there are optimal estimators. Now let's go quantum. Try to reproduce this result in the quantum regime. The scheme is the same at the beginning, but now we have the Born rule to build the conditional distribution. We are measuring an observable in general, or something in general like a P of M, for people that know what the P of M is. And we build the probability density, and then we need to perform the derivative in order to build the Fisher information. And this is usually done by constructing the so-called symmetric logarithmic derivative, which is a self-adjoint operator defined in this way, with a zero mean. Then you put everything in the Fisher information, and you have this expression in terms of the spectral measure you are performing on your system.
So what is L?
L is called a symmetric logarithmic derivative. It's an operator defined, implicitly defined by this relation, which is, by the way, a Lyapunov equation. As therefore,
But it depends on lambda.
yes, this will be a one important point. And the fact that it depends on lambda gives the name to local quantum estimation. I don't know if you know something about this classical estimation theory. We have two approaches. The global, looking for the best measurement, which is the optimal in average for all the value of the parameters. Then you have local quantum estimation theory, and then quantum estimation theory, which is looking for the optimal estimator for a given value of the parameter. This appears to be a logical loop, but I will speak about this. Okay? And so you build the Fisher information, and then by a set of inequalities, which I will skip immediately, you arrive basically at the Cauchy-Schwarz inequality in the inverse space. You arrive at this nice, very nice inequality, which say that the Fisher information of any possible quantum measurement you may perform on a system is bounded by this quantity, which is called the quantum Fisher information. So you know the maximum of the Fisher, the overall maximum over the all possible measurements is given by this quantity, which depends only on the family of quantum state you are considering, because rho lambda is explicitly there, and the symmetric logarithmic derivative is built in terms of the family of quantum states. So this is something which is essentially quantum, because in classical statistics there is no way to find the maximum, and there is not even an indication of which is the maximum. In quantum mechanics there is a way to find the maximum of the Fisher information, and this is the maximum of over all possible quantum measurement you may perform. And so there is what is called quantum Cramer-Rao inequality. The variance of any unbiased estimation is bounded by this quantity. And also there is a way to find the optimal measurement achieving this maximum, and this is the measurement for which the two inequalities are saturated. And I will see the details if the measurement satisfies this inequality in terms of they are known here are the element of the spectral measurement. And you discover that the optimal measurement is made over is the set of projectors built with the eigenstate of the symmetric logarithmic derivative. So, overall we have the answer. You have a family of quantum states. You would like to discriminate among these quantum states, or which is the same, to estimate the parameter labeling the family of quantum states, and the answer is the optimal measurement is the set of projectors given by eigenstate of the symmetric logarithmic derivative, and then, this is the measurement, then you have to process data, but the processing of data is still constant. What we are quantizing is just the measurement, but then the post-processing, you may use whatever estimator you know is optimal in this case. At least we know that the Bayesian estimator and the maximum likelihood estimator, they are. So this is the full solution. Look for this. Then we have model by model. We have to check if this can be implemented in practice, but at least we have the complete answer. And now, as somebody was noticing before, the optimal measurement of the quantity lambda depends on lambda itself. This appears to be a logical loop. And this is common, it's not original, it's not essential quantum, it's the point of local quantum distribution theory, and how this can be adapted. The first is to perform a feedback assisted measurement, or even simply, more simply, just choose a measurement, perhaps given by the measurement provided by global quantum estimation theory, have a rough estimate of the parameter on a small fraction of the copy you have at disposal, and then perform the optimal measurement, because you have an idea of which is the value of the parameter, and then you may implement the measurement of given by this recipe. Of course, you have to be sure that this iterative procedure is converging. And for this, there are no theorems. You have to check model by model. And fortunately enough, for all the examples that we have investigated, this convergence is achieved. But for this, we are not here. And then there is another possible question about all this estimation procedure is performed with the assumption that we have several repeated preparations of our quantum state, and we perform sequential measurements. And one may wonder whether entangled measure on a global preparation may be more convenient. At least for qubits, this is not true. For this, we have a theorem proved by Gill and Massara in 2000 that there is no gain in using entangled measure. And so for the estimation of a single parameter, this is the global optimum, even considering entangled measure. So, okay. So, how to solve an estimation problem? You have the family of quantum state. At first, you have to solve this equation to find the symmetric logarithmic derivative, and then plug into the quantum Fisher information. This is telling you which is the best measurement, and this is telling you which is the ultimate precision to the estimation of that value. These are operatorial solutions, because this is a Lyapunov-like equation, but of course in practice you're almost never using this construction. What you use it forced to do is to diagonalize the family of quantum state. Both the eigenvalue and the eigenvectors depends on the quantity lambda, and then you plug this in the previous formula. You have general formulas for the symmetric logarithmic derivative and the quantum Fisher information. This is nice because you have two pieces, and the idea is to maximize the Fisher information, and this is called the classical part of the quantum Fisher information. This is called the quantum part. Why? Because this is measuring how the eigenvalues of your state depends on the quantity of interest lambda, and this is capturing the dependence on the eigenvectors. Now, some example, perhaps clarifying some of the meaning of this. So the simplest example, unitary family of quantum state. You have some known state, then you are perturbing the state with a unitary perturbation. This is the generator of the perturbation, this is the quantity of interest. If G is an Hamiltonian, this is time. If G is the number of photons, this is a phase, and so on and so forth. So a general shift parameter. And the symmetric logarithmic derivative is covariant. The problem is covariant by definition. And so this is the general expression, and this is the general expression for the quantum Fisher information. There is no classical part because the perturbation is unitary, and the quantum Fisher information is independent on the value of the parameter because of the covariance. So you can measure with the same precision all the possible value of the parameter. Now let's write the Kramer-Rao bound. And the first example, when the initial state is pure. If you perform the calculation when the initial state is pure, you end up with the fact that the quantum Fisher information is 4 times the fluctuations of the generator. You plug this into the Kramer-Rao bound and you arrive at this relation. This is quite appealing for a physicist because that's the form of an uncertainty relation. But this is not an uncertainty relation. This is the Kramer-Rao bound. This is an operator, but this is a general parameter. So perhaps you have seen in the literature some heuristic uncertainty relation for time or for phase, and they cannot be proper uncertainty relation because they are not observable. And what is doing for us the Kramer-Rao bound is to give a firm statistical ground to this heuristic uncertainty relation, because this is valid also when lambda does not correspond to an observable. And when the initial state is mixed, we have 2 pieces. This is the same as before, this piece, and then we have something which depends on the fact that we are dealing with mixed state. Also, this is nice. This has not been pursued in the literature, but this is nice anyway, because it is an answer to the long-standing debate about the origin of noise in a measurement, which is the part of the noise depending on quantum fluctuation, and which is the part of the noise coming from classical fluctuation. And here we have a natural way to separate the 2 contributions. This is when the initial state is pure, so this is quantum of noise, and this is the statistical fluctuation in the propagation. Okay, then when you have your quantum Fisher information, you may build the signal to noise ratio to quantify in a more general way the estimability of the parameter, and this is the ratio between the value of the parameter and the noise. And of course, the signal to noise ratio of any possible measurement is bounded by what we may call the quantum signal to noise ratio. And this you may build several quantity as the number of measurements to achieve some given relative errors, combinations, different figures of merit to quantify the estimability of the parameter. And by this you discover that, for example, if you have a unitary parameter, and then we have already discovered that the quantum Fisher information is independent on the value of the parameter, and so the quantum signal to noise is vanishing for vanishing value of the parameter, which means that a trivial thing, if you have a parameter and the precision is constant, well, not depending on whether the parameter is large or small, then this means that this parameter is inherently badly estimated, because when it is small, the error, it remains large. But this is not a general feature. It's a feature of unitary case, but it is not a general feature. I have an example, and this is my first example of applications. And supposed to have an harmonic oscillator, which is modeling a single mode of degradation field. And you put your light beam in a noisy channel, which means the dynamical equation is the master equation. You put your oscillator in interaction with the bath of thermal oscillator at 0 temperature, and the dynamical evolution is this master equation, where this is the relation with the damping of the channel, and this is the Hilbert operator. And if you are interested in characterizing the channel, so in estimating the loss parameter, what you can do is to probe, to send some probe state, and then to perform measurement on the output state. This is nice because this is a good model for absorption of light beam and for propagation with noisy channel, at least when the temperature is very low, you don't have thermal contribution. If you apply the machinery of quantum estimation theory, you discover that the variance of the optimal estimator, which is achieved when here you perform some photon number detection and some Gaussian operation, is bounded by this quantity. And this is nice because the Campbell-Rao bound says that the variance is proportional to the loss parameter itself. So also when the loss parameter is very small, you may hope to estimate the loss parameter with high precision. Because the noise is going to 0 together with the value of the parameter. This is not counterintuitive. Think of the probability of flipping a coin. The variance of the is a Bernoullian distribution, and the variance of the event is going to 0 together with the probability of the event. It's similar to this. Then another example, the estimation of the phase in the presence of phase diffusion. Here the parameter is unitary, again a single mode of radiation field, and you are interested in estimating the phase shift, perhaps coming from a different optical path in an interferometer, and you assume that there is some noise, phase diffusion, Gaussian phase diffusion here. So the measurement scheme is the following: you have an initial state, a known initial state, then you perform the phase shift, your interferometer here, and then perhaps some noise before the measurement. But you may exchange this because the noise and the perturbation they commit. And when there is no noise, the maximum of the Fisher information is known to be achieved using here so-called squeeze state, a squeeze vacuum, and is proportional to the square of the energy. So the uncertainty in the estimation of the phase may decrease 1 over n squared, when n is the mean number of photons. What's happened when you have a phase diffusion? And of course, from the form of the noisy channel of the phase diffusion, you expect some dependence on the square root of energy, on the square of energy multiplied by the noise parameter. And this is captured by the analysis with the Fisher information, because we discover a scaling law for the Fisher information and for the squeezing fraction. When you have no noise, the squeezing fraction is 1 because the optimal state is the squeeze vacuum, and then when you have noise, you cannot appreciate the advantages of squeezing, and so the squeezing fraction is decreasing. And there are the results you discover with a tool from quantum estimation theory, and to perform a modine detection, measure the field quadrature at the output is nearly optimal, at least when the noise is very small or very high. So in this case, the optimal measurement cannot be implemented, but at least you have a benchmark to judge what can be done in quantum optics, which is homodynamic detection, basically, or photon number detection, which in this case is not useful. Now, I mentioned at the beginning that this may be applied also when the set of parameters, when the states are labeled by a set of parameters rather than a single parameter. So there is an extension to the multi-parametric case. It's quite straightforward. Instead of the Fisher information, you have the quantum Fisher information matrix. The elements are built with building a symmetric logarithmic derivative for each parameter. And the analog of the Cramer-Rao bound is given for the covariance of the estimator. In general, this inequality is not achievable. It's not attainable. It's a matrix inequality, so it cannot be achieved in general. But if you have a multi-parameter problem and you are interested in estimating a single parameter and fixed value of the other parameters, then you have this generalized Cramer-Rao inequality, and this is achievable in general. And why I'm mentioning this? Because this is the typical problem when you want to estimate entanglement of a family of quantum states. In general, you would like to estimate entanglement, but there are other parameters governing the states, other matrix elements which are relevant for the preparation of your quantum state. So you have just this kind of problem. And to introduce the problem of estimation of entanglement, just mention the simplest case. You have a pure state, and here we have a single parameter, and the entanglement is a monotone with Q. And in this case, you apply the machinery of quantum estimation theory, and you arrive at this expression for the quantum signal to noise ratio. And the meaning of this is here. And the quantum Fisher information is increasing with entanglement and diverges for maximal entanglement, which means that if you have a family of states, then when the entanglement is very large, close to 1 or to infinity, depending on the range of your measurement, and then can be estimated with high precision. This is a good news, because if you are interested in a device preparing a entangled state, then of course you would like the entanglement to be large, because the entanglements are reserves. And so you have your device preparing a state, you would like to check if you have prepared maximal entangled states or not, and your entanglement is large. And you perform the optimal measurement by quantum estimation theory, and you expect an estimation of entanglement very precise. And so you may improve your generation scheme because the estimation is very precise. Conversely, when the entanglement is low, then the quantum Fisher information is low, and so estimation of entanglement is inherently inefficient. So the error in estimating the value of entanglement is very large when the entanglement is low. And this is quite general feature. It depends on the dimension of the space, whether you have qubits, qubit, or continuous variables, but the general feature is that when the entanglement is larger, it can be estimated in a very good
that
way.
is valid for any property, this green, not only for entanglement. Estimation of small values of anything is difficult.
Well, not for the unitary case, definitely. But when I was speaking about the loss parameter of a channel, then it was the opposite. The noise was scaling as the parameter. So in that case, that's not sure. Usually, you have a fixed, the variance of your estimator is fixed. So of course, if the parameter is small, this is the measurement. But this is was not granted from the very beginning because this is a nonlinear function of the density variable. So I would say this is a result.
I see.
Unfortunately, I would have preferred another result, where the entanglement can be estimated in a good way for the whole range, but this is not the case. And this is the experimental implementation of this made at the National Meteorological Institute in Torino. They are able to prepare this family of state. This is a maximally entangled state of two, can be a maximal entangled state of any superposition of two photons of vertical and horizontal polarization. So this is a polarization entangled states. So they can tune both the parameters, the balance of the two components here and the mixing parameter, because what you have in a real device for preparing an entangled state is something mixing the entangled state with the mixture. And what we had done is to look for an estimator, a real estimator, built with some interference and visibility measurement. And what we have discovered that optimal estimation is possible. if you perform some combination here of visibility measurement, you have an estimator, and this estimator is saturating the camera. So optimal estimation of entanglement is possible, and the results are here. So here is the estimated value versus the true value of entanglement obtained because the purity parameter can be estimated independently. And in fact, we have an error also on the true value. And the gray area is the camera bound, and the blue points and line are the experimental determination together with errors. So the results is saying that optimal estimation of entanglement is possible, but of course, when the entanglement is very large, the estimation is very good, which means that the error bars are small, and when entanglement is small, the estimation, the error bars are very large. So, but this is a property of entanglement. So the good news is that optimal estimation is possible, and the bad news is that entanglement is inherently inefficiently estimated. Then my few last slides, a connection with the quantum phase transitions. And so, in general, the phase transitions in a physical system is associated with some strong change in some relative observable. So you connect the change of the state of the system with the change of some macroscopic parameter. And in quantum phase transition, you expect that to have a strong departure from the initial previous density margin. So if you have the ground state of the system, and you say that the system is experiencing a quantum phase transition, you expect the ground state to change very much from the initial. And you expect this to be quantified in terms of some distance between states in the Hilbert space. And this approach was followed by Paolo Zanardi and co-workers at the ISI Foundation a few years ago to rephrase, to reconsider the problem of identifying quantum state transition. Instead of using a macroscopic parameter, use a distance between quantum states, some kind of geometric approach to quantum phase transition. And for example, you may quantify this by the so-called Bures distance between quantum states, which is built in terms of fidelity. If you consider two ground states of a given many-body system, and you change the parameters of the interaction or of the preparation or the temperature, whatever, then you may quantify the distance between the two different ground states, infinitesimally close ground states, by the tensor metric of the Lopez distance. Now, why this is connected with quantum estimation? Because the answer is in these drawings. And when you have a set of parameters, classical set of parameters, you may induce a statistical differential manifold by considering the measurement to estimate the set of parameters. And the Fisher metric, in the multi-parametric case I was mentioning, is providing a metric. The quantum Fisher matrix is providing a metric for this statistical manifold. But the same can be done if you map the set of parameters into a family of quantum states. This was our initial starting point to define quantum estimation. And here, in the manifold of quantum states, you have distances. And the connection in between the two approaches is just the optimization. If you optimize over all possible quantum measurements you are performing here, then you arrive at the quantum Fisher metric. And the result is that the quantum Fisher metric is just proportional to the tensor metric coming from the Bures distance. So,
what is a theorem?
Yes,
It's a theorem.
or just a result of calculation. What it's saying is that the Bures metric is among the different metrics you may define on the manifold of quantum state. The Bures metric is capturing the statistical distinguishability. The other distances perhaps are capturing something else, but the statistical distinguishability in terms of measurement is captured by the Bures metric. And this is telling you something which is after all quite trivial, that if you have a parameter labeling the ground state of a many-body system, then the estimation of this parameter is very effective at critical points. This is something, it sounds, but then we have some analytical proof of this intuition. And in fact, you may, I'm skipping details, but you may perform analysis on some super extensive behavior of the quantum Fisher information with respect to the size of the system, of the temperature, quantifying this statement that estimation is very effective at critical points. Just an example before going to the end. Take the simplest example, the Ising model with the transverse field. And suppose you would like to estimate the coupling constant. You have a chain of spins, and you would like to characterize the system, which means to estimate the value of the coupling. And what you discover that the quantum Fisher information at zero temperature is maximized at the pseudo-critical point for any n. This is a result, because for finite size, this is not a critical point. What is called the critical points, you have only one for thermodynamical limit. But here, the result is that even when the size is finite, the quantum Fisher information is maximized at a pseudo-critical point, and you have a super extensive behavior of the quantum Fisher information. And another nice result, I would say, is that one may wonder, but the measurement achieving this quantum Fisher information is feasible? In general, no. It is a complicated expression in terms of the symmetric logarithmic derivative that does not correspond to something maybe implemented in practice. What you can measure on a spin chain is the total magnetization. This can be measured. And what you discover is you perform the ratio of the Fisher information of this measurement to the quantum Fisher information, then at least when the coupling is not too small, the ratio is 1. So also in this case, in some regimes, you have that the Kramer-Rao bounds can be achieved, so optimal estimation can be achieved. So, summary. Let's make this short. Quantum estimation is a tool for quantum technology because there are several quantities of interest which are not corresponding to observables. So we need something more that postulates quantum mechanics to attack the problem. And the recipe is quite clear, and you have also a benefit of being quantum, that you know the maximum of the Fisher information, and you have the full recipe to arrive at the optimal estimation, and either to implement the optimal estimation scheme, or to use it as a benchmark to judge what can be implemented on your system. And then there are few more results about the estimability of the parameter, and about this is a bit not explored, and I have no time to present result about the classical and quantum contribution to uncertainty. Thank you very much.
Questions?
A good measure of the noise to signal ratio is the Mandel parameter sum of factors. Can you relate that to the quantum Fisher information, some connection?
At least, yes. Well, of course, on a restricted set of physical systems, basically the radiation field.
Yes.
Where the final factor has an immediate meaning in terms of classicality and non-classicality.
Yes.
In that case, yes. In general, no, because the final factor for a finite dimensional system is not immediately related to any quantumness. So,
but for the radiation field? For
the radiation field, yeah, definitely, the answer is yes. I don't know the complete answer, but I'm quite sure it can be.
Any other question? I would like just at the very beginning, just to clarify things. which is the physical meaning, just repeating, if you already told about this inequality, you already passed it. Okay, about this f of lambda, the Fisher information is less than the quantum Fisher information, which is the physical meaning. Yes.
Okay, the Fisher, this is defined here.
Yes, with the conditional probability of
Yes.
lambda.
So the Fisher information can be then evaluated once we have chosen a measurement. So among all the possible measurements you may perform on a system, you choose one. And then the precision in the estimation of a given parameter starting from that sample of measurement is ruled by the Kramer area. You want to maximize this. And the other inequality, the quantum Kramer inequality, says that choose one measurement and choose another one, you compare them. But the Fisher information of any measurement you may perform on a quantum system is anyway bounded by this quantity. So if you choose a measurement whose Fisher information is equal to the quantum Fisher information, then you cannot do better than this. So it's just saying that this is nice because basically the set of quantum measurements is well characterized. You have self-adjoint operator, spectrum measure, or POVM. The set of classical measurements performed on a physical system is not well characterized. What is a measurement in classical physics? It's a distribution. But then a distribution in which space? Which constraints you put on your distribution to be physically admissible? It's not completely clear. There is no classical theory of measurement in this sense. In quantum mechanics, we have quantum theory of measurement. They have the full characterization, POVM. And this fact made possible to write down, to obtain the ultimate maximum of the Fisher information. This is not possible in classical physics.
Can I have another? Can you say something more about contribution to quantum and classical contribution to uncertainties?
Yeah, yes. Of course, here. Of course, this is valid for unitary parameter. We have a unitary perturbation. This is so. This is the starting point, and then you ask about the contribution to noise. So when the state is pure, everything is quite clear, and this is what you obtain when the state is present. It's nice because we have a sum, but it's bad because this operatorial form is not easy to handle. This is why everybody is saying very nice, but then nobody is working on this subject.
Yeah.
Because nobody found a way to deal with all this operatorial kernel and so on and so forth. So in principle, the answer is there, but then I tried sometimes and then I fail. Other person.
Yeah, it looks difficult. Thank you.
Just the last, you have shown this estimation of entanglement for qubits respect this respect anything senior for continuous variables, or just very specific results?
No, yes and no. We already did on paper the attack the problem. We know the ultimate bounds, we know everything. But then in that case, what can be done in a lab for the moment is not achieving the maximum. So you have a way to estimate entanglement that is much more noisy than the ultimate bound provided by the Kramer inequality. So for the moment, of course, entanglement for continuous value can be estimated, but nobody found a way to separate. Because the set of possible measurements on the continuous variables is restricted. I mean, you have an infinite number of parameters, and then you may just count photons or measure the field, the real field, or the complex field.
Any other question? So if not, it's time to see you.